Helicoprion. In 1897, a rancher cracking open a limestone slab in a quarry near Crookston, Idaho, pulls out something that stops him cold. It is a perfect spiral of teeth. Not scattered teeth, not a jumbled fragment, but a coiled interlocking whorl, each blade larger than the last, stacked outward like a nautilus shell cast in bone. It is immaculate. It looks less like a fossil and more like a piece of precision machinery dropped by something that had no business existing. He shows it to the world. The world's best paleontologists spend the next 125 years arguing about where on the animal's body it belonged. This is Helicoprion, Greek for spiral saw, and the argument it started is one of the strangest in the history of paleontology. The fossil was formally described by Russian geologist Alexander Karpinski in 1899. What he had was a whorl of 117 interlocking teeth, some measuring 10 centimeters individually, the full spiral reaching up to 45 centimeters in diameter in the largest known specimens. What he did not have was a skull. No jaw, no skeleton, just the teeth. And from that single structure, scientists attempted to rebuild a predator that had been dead for 270 million years. The reconstructions that followed are a catalog of increasingly creative guessing. One proposal put the whorl spiraling outward from the snout like a sawfish. Another placed it on the dorsal fin. A 1966 illustration that became widely reproduced showed the spiral curving up and forward from the tip of the nose like a rhinoceros horn attached to a shark. Each version was drawn with confidence. Each version was wrong. For over a century, the animal appeared in scientific literature and museum displays in a form that its own fossils did not support. What makes Helicoprion more than a curiosity is the global reach of its bones. Specimens have been found in Idaho, Russia, Kazakhstan, Australia, and Japan. Over 100 specimens documented across what were once vastly separated Permian seas, suggesting an animal with near global distribution. The size estimates that emerged from this material were striking. Helicoprion is believed to have reached approximately 7.5 meters in length, making it one of the largest predators in the Permian Ocean. And yet, for all of that, the fundamental question of anatomy remained unresolved for longer than the United States has existed as a country. The answer finally came in 2013. Leif Tapanila of Idaho State University applied CT scanning to a specimen still embedded in its surrounding rock matrix. The scan revealed something that surface examination had never shown: preserved cartilage surrounding the whorl, placing it definitively in the lower jaw, recessed back toward the throat. The 2013 paper, published in the journal Biology Letters, resolved a mystery that had stood since Karpinski's original description. 114 years of wrong answers, corrected by a scanner and a slab of Idaho limestone that hadn't been fully examined. The mainstream explanation for the whorl is now well supported. Helicoprion was not a true shark in the modern sense, but a holocephalian, a relative of the ratfish. Because holocephalian skeletons are made of cartilage rather than bone, they almost never fossilize. The whorl was retained permanently, never shed the way a shark sheds teeth, and it functioned to process soft-bodied prey. Ammonites, squid. The mechanism pulled them in and compressed them. The biology, once the jaw placement was confirmed, made functional sense, but the 2013 study also revealed something that the textbooks mention quietly, if at all. Helicoprion had no upper teeth. None. The upper jaw was essentially toothless, which means the entire mechanism, that perfect spiral of blades, moved against a smooth upper surface. There is no living animal that hunts this way. No analog, no descendant, Nothing in 500 million years of vertebrate evolution has arrived at the same solution. Scientists built models, ran simulations, confirmed it worked, and then mostly moved on. What they haven't fully answered is why. Why did this design appear, dominate Permian seas across the entire planet, and then vanish in the extinction event at the end of the Permian without leaving a single lineage behind? Not a diminished version, not a distant cousin, nothing. The spiral saw appeared, ruled, and disappeared as completely as if it had never existed. We know what it was. We still don't entirely know what it means. From a fossil that spent a century misidentified in a quarry wall, we moved to a discovery that rested in the ground for 390 million years before a single claw fell out of a German quarry and forced scientists to reconsider the upper limit of what the sea could build. Jacalopterus. The year is 2007. A team working a quarry near Prüm in the Rhineland of Germany uncovers a fossilized claw, not a small one. This claw measures 46 centimeters in length, bigger than a human face. The researcher who finds it, Marcus Poschmann of the Mainz Museum of Natural History, does the arithmetic almost immediately. If the proportions of the claw match the known body plans of its closest relatives, then whatever this came from was approximately 2.5 meters long, the size of a large crocodile. His colleagues tell him the number is almost certainly wrong. Jacalopterus rhenaniae was a sea scorpion. Eurypterids, the group it belongs to, were already known to science. Smaller members had been documented for over a century, and they were considered well understood. But nothing in the existing record had prepared anyone for a claw that size. When Poschmann and Simon Brady published their analysis in Biology Letters in 2008, they made the case carefully. Using scaling ratios drawn from closely related species, the total body length of the animal that produced this claw was approximately 2.5 meters, making Jacalopterus the largest arthropod in the fossil record. The largest joint-legged animal, including every insect, spider, crab, and centipede that has ever been documented in the history of life on Earth. The size was staggering enough. But what made the pushback from some corners of the scientific community sharper than usual was a second problem, a metabolic one. The standard explanation for giant arthropods invokes oxygen. During the Carboniferous period, atmospheric oxygen peaked at roughly 35% compared to today's 21%. Higher oxygen levels allow the passive diffusion system that arthropods use to breathe to supply larger bodies. That is why Carboniferous forests produced millipedes the length of a car and dragonflies with wingspans approaching 70 centimeters. But Jacalopterus lived in the Devonian approximately 390 million years ago in oxygen conditions estimated to be comparable to our own. The high oxygen excuse was not available. This sea scorpion was enormous without the atmospheric conditions thought necessary to make enormous arthropods possible. The Devonian seas where Jacalopterus lived were not peaceful. This was the age of armored fish, of the great placoderms, of predator ecosystems more complex than anything that had come before. Jacalopterus had paddle-like rear limbs suited for active swimming and front claws clearly adapted for capturing prey rather than filter feeding. It was not a scavenger drifting through shallow water. The body plan implied speed and pursuit. And in an ocean that also contained large armored fish, the existence of a 2.5-meter arthropod at the top of a separate predatory line suggests a Devonian sea considerably more dangerous than most reconstructions convey. Eurypterids as a group showed a size range across their species that remains one of the most extreme in invertebrate paleontology, from animals roughly 10 centimeters long to this. The same body plan, scaled across 25 times in length. They survived for over 200 million years before going entirely extinct in the Permian mass extinction approximately 252 million years ago. Not diminished, not transitioned into something smaller. Gone completely and permanently, leaving no descendants in any living lineage. The mainstream position is that the claw estimate is methodologically sound. Comparative morphology from related species supports the scaling, and the result, while extreme, falls within what aquatic arthropod biology can theoretically sustain. Buoyancy in water offsets the structural cost of an exoskeleton that would be impossible on land. But here is the problem that the formal paper cannot entirely sidestep. We have one claw. The entire reconstruction, the body length, the predator designation, the title of largest arthropod in Earth's history rests on a single fragment. No torso, no head, no confirmed full skeleton anywhere in the world. The scaling logic is sound, but scaling from a single element has produced dramatically wrong reconstructions before in paleontology. And the deeper question, the one that nobody has cleanly answered, is why this is the only evidence of Jekyllopterus that has ever been found. If it was genuinely this large and genuinely this widespread, where is everything else? Some researchers have suggested the Eurypterid fossil record as a whole is far more incomplete than the number of known specimens implies. Most of what we have is fragmentary, preserved by geological accident. The possibility that we have found the claw of a species that was once common and whose full anatomy would rewrite the picture of Devonian seas is not something the literature rules out. It just doesn't dwell on it. From a single claw in a German quarry, we descend into the coal forests of a much later world, where the problem was not the sea, but the land itself, and an animal so large that scientists spent decades trying to explain how it breathed. Arthropleura. Imagine walking through a coal forest 340 million years ago. The trees are not the trees you know. They are giant club mosses and horsetails, some reaching 30 meters, crowded so tightly the canopy is almost solid. The air is thick, heavy with oxygen. The forest floor is wet and dark. And moving through it, pressing parallel tracks into the soft sediment, is something approximately 2.5 meters long and half a meter wide. It moves on dozens of legs. It is the largest land arthropod that has ever existed, and for most of the history of paleontology, scientists could not agree on how something that size could have been physically possible. This is Arthropleura, and it was found in pieces before anyone understood what it was. The trackways came first. In the 19th century, geologists in Nova Scotia began finding long parallel impressions in ancient sandstone, evenly spaced rippling marks consistent with a large segmented animal moving in an S-shaped pattern. Nobody knew what made them. Then, in Scotland and Germany, researchers found fragments of the animal itself. Armored plates as wide as dinner platters, clearly belonging to a multi-segmented body of extraordinary size. Arthropleura was formally described from this material in the 19th century, but the picture remained frustratingly incomplete for well over 100 years. The most recent major discovery came in 2021, when a remarkable trackway was found in Northumberland, England, preserved inside a boulder that had fallen from a coastal cliff. Neil Davies and colleagues at Cambridge University published the finding in the Journal of the Geological Society. The animal that made it, they estimated, was approximately 2.5 meters long and weighed in the range of 50 kilograms, comparable to a large dog. On legs. The standard explanation for Arthropleura's size points to carboniferous oxygen levels. Robert Berner of Yale University, among others, has estimated that atmospheric oxygen during the Carboniferous peaked at approximately 35%, significantly higher than today. Arthropods breathe through a passive system of tubes and openings called tracheae and spiracles. At normal oxygen concentrations, this system cannot supply enough gas to sustain a body mass of 50 kilograms. At 35%, the math improves considerably. The high oxygen atmosphere in this view is what opened a door that stayed open for roughly 60 million years and then closed permanently, when the Carboniferous rainforest ecosystems collapsed around 300 million years ago, in the event paleontologists call the Carboniferous rainforest collapse. The dense coal forest fragmented. The habitat that had sustained Arthropleura contracted and broke apart. Oxygen levels fell. The giant millipede disappeared from the fossil record approximately 280 million years ago. In the mainstream account, it is a clean story. Environment enabled the animal. Environment removed it. But the 2021 Northumberland discovery introduces a wrinkle. The Northumberland Trackway pushes Arthropleura into conditions, both in geological time and geography, that do not fit the high oxygen model as neatly as the textbooks suggest. The trackway dates to approximately 326 million years ago and was found at what was then an equatorial latitude. The timing and location both point toward conditions somewhat different from the peak oxygen, cool temperate environment the standard narrative assumes. Some researchers have noted this quietly. The popular explanation may be slightly too tidy. What the record does not offer, and this is the strangest gap of all, is a complete specimen. We have trackways, we have armored plates, we have enough fragments to establish the body plan. But no one has ever excavated a whole Arthropleura. We have never clearly seen its head. We do not have a confirmed leg count. We have never seen its sensory organs. The animal whose fossilized tracks we can follow across 340 million years of stone remains, in its full anatomy, unknown. Analysis of gut contents from partial specimens has suggested Arthropleura was a herbivore or detritivore, feeding on decaying plant material and possibly fern spores. It was not hunting anything. It was the largest land arthropod in Earth's history, and it spent its existence eating plants in a forest that no longer exists. The largest living millipede today reaches roughly 38 centimeters. The gap between that and 2.5 meters is not a gradual scaling. It is a discontinuity. A size that persisted for 60 million years, and then was gone so completely that nothing since has come close. From the dark forests of the Carboniferous, we cross to the late Devonian seas and an animal that had no teeth at all, but didn't need them. Dunkleosteus. The late Devonian Ocean, 360 million years ago, is not a place you want to be. The reefs are dying. The extinction event that will eventually erase more than 70% of all species is already beginning at the edges. And moving through the warm coastal shallows of what is now Ohio is a fish approximately 8 to 9 meters long, armored from the head to the midpoint of its body in interlocking plates of bone, and equipped with a jaw that has no teeth, not a single one. Instead, 2 interlocking plates of self-sharpening bone that grind against each other like scissors every time it closes its mouth, creating edges that stay sharp precisely because they wear against one another. The jaw opens in approximately 1/50th of a second. The suction generated is sufficient to pull prey inward before any muscular reaction can resist it. When scientists ran the numbers, several of them said the numbers were wrong. Dunkleosteus terrelli was first excavated in significant quantity from the Cleveland Shale in Ohio beginning in the 1860s, and the animal was formally named in 1956 in honor of David Dunkel of the Cleveland Museum of Natural History. For decades, it was understood as a large armored fish. The true picture of what its jaw was capable of did not emerge until 2007, when Philip Anderson and Mark Westnett published a detailed biomechanical analysis in Biology Letters. Their models calculated a bite force of approximately 7,400 newtons at the jaw tip, rising to 11,000 newtons toward the rear of the jaw, placing Dunkleosteus among the most forceful biters of any fish in the fossil record. The jaw opening speed they calculated, 1/50th of a second, generated a negative pressure sufficient for suction-based prey capture. When these figures were published, several researchers flagged them as implausibly high for a Devonian plesioderm. The bones had to wait for the biology to catch up. What makes the jaw mechanism genuinely strange is not just the force, it is the design. The self-sharpening property of bone-on-bone shearing has no equivalent in any living vertebrate. Every predatory fish alive today has teeth. Dunkleosteus solved the problem of cutting prey without a single tooth ever growing in its mouth. The edges formed naturally through use, maintaining their geometry through wear rather than replacement. It is an engineering solution that vertebrate biology arrived at once in the Devonian and never returned to. The evidence for what Dunkleosteus was eating comes directly from the fossils. Partially digested prey, boluses have been found associated with Dunkleosteus specimens, compacted masses of bones and scales from other fish, including early sharks. Dunkleosteus was not eating what its era considered small prey. It was eating the other apex predators. The things swimming at the top of the Devonian food chain were themselves being hunted by something armored and boneless-jawed that moved faster than they could react. Dunkleosteus was a placoderm, a class of armored fish, and the placoderms as a group went entirely extinct in the end Devonian mass extinction approximately 359 million years ago. They left no descendants. The class that included the most powerful jawed fish in the Devonian Ocean vanished without transition, without survivors, without a reduced or diminished lineage carrying any part of the design forward. But the fossil record for Dunkleosteus has a structural problem that the museum displays don't advertise. The armored skull and thoracic shield of Dunkleosteus preserve extraordinarily well. Dozens of specimens exist. The rear half of the animal, the unarmored body, has almost never been clearly preserved. Every body length estimate, every weight calculation, every reconstruction you have ever seen of this animal is a projection from the armored front section onto an unknown posterior. Different researchers applying different scaling methods to the same skull have produced total body estimates ranging from 6 to 10 meters. We have hundreds of faces. We have almost nothing behind them. What the bones say is real. What exactly those bones were attached to remains, after 160 years of excavation, genuinely uncertain. From the armored executioner of the Devonian shallows, we move 60 million years past the dinosaur extinction to the tropics of South America, where a snake was pulled from a coal mine and forced climate scientists to revise an entire geological epoch, Apis Titanoboa. In 2009, a team from the Florida Museum of Natural History is working in the Carrijon open-pit coal mine in La Guajira province in northern Colombia. The mine has been known as a rich fossil site. The Paleocene epoch, the period beginning roughly 6 million years after the extinction of the non-avian dinosaurs, is poorly understood in South America. The team is excavating carefully when someone uncovers a vertebra. A single vertebra. It is roughly the size of a dinner plate. Jonathan Block, the team's vertebrate paleontologist, picks it up and does the calculation that any vertebrate paleontologist would immediately attempt. If this bone is proportional to the spine of a modern boa constrictor, the animal it belonged to was approximately 13 meters long. It weighed over 1,000 kilograms. It is the largest snake that has ever existed, and its existence, Bloch and his colleague Jason Head would soon publish, meant the Paleocene tropics were several degrees hotter than the climate models said they were. Titanoboa cerrejonensis was formally described in a paper published in Nature in February of 2009. The size estimate, derived from vertebral dimensions compared to modern boas and anacondas, placed the animal at approximately 12 to 14 meters in length, with a mass somewhere in the range of 1,100 kilograms. For comparison, the largest living anacondas, the heaviest snakes alive, reach approximately 8 to 9 meters and around 250 kilograms. Titanoboa was not a slightly larger version of a living snake. It was a different category of animal. The implications didn't stop at the snake. The body size to temperature relationship in large tropical ectotherms is well established. Cold-blooded animals are limited in maximum body size by ambient temperature because their metabolism depends on environmental heat. Head and Block applied this relationship to Titanoboa and arrived at a required mean annual temperature for the Columbian Paleocene of between 30 and 34 degrees Celsius. The existing climate models for that period placed Paleocene tropical temperatures at approximately 28 degrees. When the paper was published, climate scientists pushed back. The snake's size was calling their models wrong. Eventually, after several years of revised analysis, the models were adjusted. The snake had been right. The Cerrejon Formation has been extraordinarily generous since that first vertebra. The site has yielded fossil material from multiple Titanoboa individuals, alongside giant Paleocene turtles and large crocodilians, suggesting an entire ecosystem scaled upward by heat. The same formation also contains the oldest known tropical rainforest ecosystem in the Americas. Cerrejon is not just a snake site. It is a window into a world that most reconstructions of the post-dinosaur period had not imagined. The mainstream account of Titanoboa is now settled in its broad outlines. A warmer than previously reconstructed Paleocene, the absence of large dinosaurian competitors, and a rich tropical ecosystem combined to produce the conditions in which an ectotherm of this mass could be sustained. The size is dramatic but not mysterious. It is a consequence of conditions, but the revision that happened is worth sitting with. A set of vertebrae pulled from a Colombian coal mine did not just establish a new species record, it forced a recalculation of what the Paleocene tropics actually looked like. Not a new isotope study, not a new deep-sea core, a snake. The feedback from that correction runs in both directions. If the Paleocene tropics were genuinely 30 to 34 degrees, then Titanoboa's world is a direct prehistoric analog for what a significantly warmer modern tropics might look like. Giant crocodilians, giant turtles, a snake that outweighs a car. Some researchers have noted this connection carefully. Others have preferred not to linger on it. A few scientists have also quietly raised a more fundamental methodological question. The formula that links snake body size to ambient temperature was derived from modern snakes. Whether it can be reliably applied to a species 60 million years removed, with potentially different physiology and behavior, is not something the fossil record can confirm. The calculation might be exactly right, or it might be a very close approximation of a truth we cannot quite reach from the evidence we have. From the coal mines of Colombia, we cross an ocean and move through 12 million years to a desert in Peru where a skull was waiting in the sand. Leviatan Melville. The Ica Desert in southern Peru is one of the driest places on Earth. It receives almost no rainfall. Almost nothing lives there. And beneath its surface, preserved for millions of years in what was once the floor of the ancient Miocene Pacific, lies some of the richest marine fossil material anywhere in the world. In 2008, a team of European and Peruvian paleontologists prospecting in the Pisco Formation pulls a skull from the sediment. It is 4 meters long. It belongs to a sperm whale, but it is not the sperm whale you know. This one has enormous functional teeth in both its upper and lower jaw, each tooth up to 36 centimeters in length, the largest teeth of any animal in the fossil record. The researchers name it after the biblical sea monster Leviathan and the author of Moby Dick. Then they spend the next several years trying to explain why a whale would need a weapon in its upper jaw. Leviathan Melville was formally published in Nature in June of 2010, authored by Olivier Lambert of the Royal Belgian Institute of Natural Sciences, Christian de Muison of the Natural History Museum in Paris, and colleagues. The genus name was slightly adjusted after the formal submission process revealed the original name was already occupied in zoological nomenclature, but the animal and its implications remained unchanged. A physeteroid, a sperm whale relative, reaching an estimated 13 to 17 meters in body length, with the largest teeth recorded for any animal in the history of life. The problem the teeth create is not cosmetic. Modern sperm whales have teeth only in the lower jaw. The upper jaw is soft, flexible, and essentially toothless. This is not a primitive condition or a developmental gap. It is an adaptation. The toothless upper jaw allows a modern sperm whale to engulf prey whole. Leviathan, with massive interlocking teeth in both jaws, could not engulf prey the same way. It bit, it gripped, it tore. This was active dismemberment of prey at scale, an attack mode that no living great whale uses and that was previously considered biologically implausible for an animal this size. The skull also contained a large spermaceti organ basin, the hollow structure associated with the biosonar system that modern sperm whales use for echolocation. Leviathan, in other words, was simultaneously equipped to find prey by sound and to kill it with the largest teeth any animal has ever grown. The combination has no living equivalent anywhere in the ocean. What makes the geography of the discovery particularly striking is the fauna surrounding the fossils. The Pisco Formation in the Miocene was not an isolated ecosystem. The same ancient Pacific that yielded Leviathan also yielded evidence of Megalodon, the enormous megatooth shark. Both animals, the two largest macro-predators in Earth's history by any reasonable measure, appear to have occupied the same ocean at the same time. Researchers have noted this overlap carefully. Whether the two competed directly, whether they partitioned prey, or whether one or both were responsible for the other's eventual disappearance, the fossil record does not say clearly. The mainstream explanation for Leviathan places it firmly in an evolutionary context. Physeteroid whales included multiple large macro-predatory forms in the Miocene, and Leviathan represents the extreme end of that radiation. Its functional upper teeth are an earlier evolutionary stage, before the modern sperm whale lineage reduced upper dentition. Its extinction in the late Miocene correlates with ocean cooling and shifts in the prey base. A coherent story. But there is a detail in the skull that some researchers have raised without a clean resolution. The spermaceti organ basin in Leviathan's skull was disproportionately large even relative to its body size, larger than expected even for a whale of this mass. Some researchers studying modern sperm whale biology have proposed that the spermaceti organ may function in part as a battering instrument in social competition. If Leviathan used its organ the same way, then it possessed a predatory toolkit combining sonar, crushing bite, and potential ramming capability. An attack architecture with no parallel in any living marine predator, before or since. Whether that is what the fossil is actually showing, or whether we are projecting function onto anatomy, is precisely the kind of question the evidence available cannot answer. We stay in the ancient tropics, but we cross from the Pacific to the rivers of Miocene South America, Where something was waiting with a bite force the calculations said could not be right. Purosaurus 8 million years ago, western Amazonia does not exist in the form you know. The Amazon River has not yet been born. In its place is a vast inland sea, a continent-wide system of shallow, warm wetlands stretching from the base of the still-rising Andes to the Atlantic, fed by seasonal floods and dense with life at every level of the food chain. It is called the Pebos mega-wetland system. And, moving through its shallows, pressing deep impressions into the mud, is a crocodilian 12.5 meters long, weighing approximately 11 tons, with a skull the size of a dining table. When researchers applied finite element analysis to that skull, the calculated bite force came out at approximately 69,000 newtons. They checked the numbers, they published them. Some colleagues in the biomechanics community checked the methodology and asked whether the figure was too high. The figure held. Purosaurus brasiliensis was first described from fragmentary material found in the Solimois Formation in 1892. But the full picture of its size and mechanics took over a century to assemble. The definitive biomechanical analysis was published in the journal PLOS I, using three-dimensional finite element analysis of the skull, the same engineering technique used to model stress in bridges and aircraft fuselages. The number it produced, 69,000 newtons, is the highest bite force calculated for any animal in the fossil record. For comparison, a saltwater crocodile, the most powerful biter among living reptiles, generates approximately 16,000 newtons. A great white shark, approximately 18,000. Tyrannosaurus rex, depending on the study, somewhere between 35,000 and 57,000. Purosaurus exceeded them all. The skull that produced this number measures approximately 1.5 meters in length in the best preserved specimens. Multiple species have been identified within the genus: Purosaurus brasiliensis, Purosaurus mirandai, and Purosaurus neivensis, suggesting the group was not a single isolated giant, but a lineage of large apex predators that dominated the Pebos wetlands for several million years. The formation that contains them also yielded giant river turtles with shells over a meter wide, anaconda relatives of substantial size, and a diverse fish fauna. A prey base theoretically capable of sustaining an 11-ton predator, at least in principle. The mainstream account of Purosaurus is that it was an unchallenged apex predator of the Miocene wetland system. When the Andes reached their current height and redirected drainage eastward, the Pebos system drained, the inland sea became the Amazon basin, and the extraordinary wetland productivity that had sustained a crocodilian of this size collapsed. Purosaurus went extinct approximately 5 million years ago. Habitat change, not competition, ended it, but the bite force figure creates a problem the functional morphology community has not fully resolved. 69,000 newtons is approximately double the force that would have been necessary to process the largest documented prey in the Pebos Formation. The biggest turtles, the biggest fish, the biggest potential prey animals available in that environment would have required roughly half that force to subdue or crush. Overkill is rarely a stable evolutionary strategy. Structures are metabolically expensive to build and maintain. An organism does not generally evolve a jaw apparatus far beyond what its available prey demands. So what was Purosaurus biting that required 69,000 newtons? Some researchers have proposed that the extreme bite force was used primarily in intraspecific combat, the fighting that occurs between members of the same species over territory and reproduction. Living crocodilians show healed bite wounds from conspecific conflict at relatively high rates, and the forces involved in fighting another large crocodilian can exceed those required for prey capture. If the Pebos wetland supported multiple Purosaurus individuals, and if the competition between them was intense The jaw might have been optimized not for hunting, but for fighting itself. The monster was not pursuing something larger. It was competing with a mirror. Whether that explanation fully accounts for the number, or whether there were prey animals in the Pebus system we have not yet found, remains open. What is not open is the force itself. The bones produced the number. The bones were right. From the inland sea of Miocene South America, we traveled to the frozen Arctic, and a skull pulled from permafrost that triggered a public argument before the paper was even published. Predator X. The Svalbard archipelago sits halfway between Norway and the North Pole. In summer, the sun does not set. In winter, it does not rise. The permafrost beneath its surface preserves material with an efficiency that few environments on Earth can match. In 2006, Jørn Hurum of the University of Oslo Natural History Museum begins excavating a site in the Slottsmoya member of the Agardfjellet Formation on the island of Spitsbergen. What emerges over 2 field seasons is the most complete large pliosaur material ever found. Skull sections, jaw fragments, limb bones, vertebrae. The skull alone, in preserved length, measures close to 2 meters. A preliminary estimate of the total skull size reaches nearly 3 meters. Hurum calculates a body length of approximately 15 meters. The bite force estimate, developed from skull dimensions, enters the popular science press as 33,000 pounds per square inch. His colleagues, several of whom have not seen the material, call the figures irresponsible. The debate begins before the formal paper exists. The animal was informally called Predator X during the excavation and publicity period and was formally described as Pliosaurus funke by Hurum and Patrick Druckenmiller in the Norwegian Journal of Geology in 2012. By the time the formal description appeared, the size estimates had been revised. The body length figure moved toward the lower end of the range, closer to 10 to 13 meters, based on more rigorous proportional analysis. The bite force in the peer-reviewed literature settled at approximately 33,000 newtons at the tooth tip, still placing it among the highest calculated for any marine reptile, but considerably below the PSI figures that had circulated in media coverage. Pliosaurs were not obscure animals. The group had been known for over a century, with famous examples including Kronosaurus and Liopleurodon, and all of them shared the same essential blueprint. A massive barrel-shaped body, a short neck, a long, powerful skull, and 4 equal-sized paddle limbs enabling the 4-point propulsion that allowed rapid acceleration in open water. What made the Svalbard material different was completeness. Previous giant pliosaur discoveries had been frustratingly fragmentary. Skull pieces, isolated limb bones, a vertebra here and there. Pliosaurus funke was represented by material sufficient to actually work with, to model, to test. The Svalbard Formation that yielded Predator X has produced multiple large marine reptile species, ichthyosaurs, plesiosaurs, and pliosaurs coexisting in what were clearly productive late Jurassic Arctic waters. The environment 147 million years ago was dramatically warmer than today's Arctic, supporting ecosystems rich enough to sustain multiple lines of large predators simultaneously. What Predator X was hunting in those waters, how it partitioned prey with other large predators in the same formation, and whether it was the top of that particular food chain or one of several apex predators sharing the same ocean, remains poorly understood. The mainstream response to Predator X resolved the controversy in a specific way. The extreme media-circulated figures were preliminary, not peer-reviewed, and should not have been treated as established. The formal 2012 paper corrected them. Science worked as it should. The criticism of the initial figures was legitimate, and the revision was appropriate. But there is something worth examining in how the correction was received. The informal predator X estimates were publicly attacked by researchers who had not seen the material. When the formal paper appeared with revised but still extraordinary figures, the dominant narrative in popular science had already calcified around the idea that the animal had been exaggerated. The corrected version, a 10 to 13 meter pliosaur with the highest calculated bite force of any known marine reptile, largely disappeared beneath the story of the numbers that had been walked back. The real animal was buried under the correction of the preliminary one. Some paleontologists have noted that the Svalbard pliosaur record is likely substantially incomplete. Arctic permafrost both preserves and conceals material in ways that make systematic excavation difficult, and the diversity of large marine reptile species in the same formation suggests an ecosystem that supported far more biomass than the current specimen count implies. If Pliosaurus funke was relatively common in late Jurassic Arctic seas, the material recovered so far may be the beginning of the record rather than its extent. What additional specimens might change about the reconstruction, we do not yet know. From the permafrost of the Norwegian Arctic, we travel south and forward in time, across the extinction of the dinosaurs and into South America, where something filled the apex predator vacancy in a way that biomechanists initially said was physically impossible. The terror bird. 62 million years ago, the dinosaurs are gone. The extinction event that ended the Cretaceous has cleared the largest ecological slots on the planet. In South America, isolated from the northern continents by a gap of open ocean, something steps into the vacancy. It does not have 4 legs. It cannot fly. It stands 3 meters tall. Its skull, the size of a horse's head, ends in a hook, a massive compressed beak that curves downward to a point. When researchers in 2010 applied finite element analysis to a related skull, the kind of structural stress modeling used to test engineering designs, they found that the skull was optimized for a specific attack mode, lifting the head and driving the beak downward into the prey's skull in a single vertical strike, the way an axe falls. And when they presented this finding, several ornithologists said a bird's skull could not absorb the rebound force of that kind of impact. It would shatter. The stress modeling said otherwise. The skull was built precisely for the blow that should have broken it. The family, Phorus, Racidae, the terror birds, first appeared in the Paleocene approximately 62 million years ago and persisted in South America until roughly 1.5 to 2 million years ago, a span of 60 million years during which they dominated as apex predators across a continent that lacked large mammalian carnivores entirely. The most complete large species, Kelenken guillermois, was formally described in 2007 from Patagonian material and possessed a skull measuring 71.5 centimeters in length, the largest bird skull in the fossil record. Leg bone proportions suggest running speeds in the range of 48 to 65 kilometers per hour, comparable to a modern ostrich. It was fast, it was large, and according to the 2010 analysis by Federico de Grange and colleagues at the National University of Córdoba, it struck its prey in a manner no living bird employs. The de Grange study modeled 3 possible attack behaviors on the skull of Andalgalornis stuleti, a medium-sized Phorus racid. Lateral pulling, the way most large predatory birds kill prey, generated stress concentrations that the skull architecture would not have tolerated. Shaking produced similar structural problems. The vertical hatchet strike driving the beak downward with the neck and body behind it distributed stress evenly across the beak and skull. The animal was not built to grab and thrash, it was built to execute. The biomechanical signature of its anatomy pointed toward a killing behavior with no living analog. The family's record in South America is extraordinary in its duration. 60 million years of apex predator dominance, surviving every extinction event and ecological shift the South American Paleogene and Neogene could produce until the formation of the Isthmus of Panama approximately 3 million years ago allowed placental mammals from North America to cross into the continent for the first time. Titanus whalleri, the only Forus racid confirmed to have crossed in the other direction, is documented from Texas and Florida. 3-meter predatory bird reaching North America, moving into a continent already occupied by mammalian carnivores and apparently persisting for hundreds of thousands of years before disappearing. The mainstream account of the terror bird's extinction is competitive displacement. The arrival of large placental carnivores, including ancestors of modern jaguars and other cat lineages, introduced a predator type that Forus racids had never coexisted with in 60 million years. The combination of pressure from multiple new competitors ultimately overwhelmed a lineage that had been unchallenged for most of its existence. But the longevity is what refuses to sit quietly. A family of predatory birds that outlasted the entire period from the extinction of the dinosaurs to the present day. A body plan that biomechanics initially said was mechanically impossible. An animal that crossed a continental barrier and held its own in an unfamiliar ecosystem. The terror birds were not a failed experiment or a brief evolutionary curiosity. They were one of the most successful apex predator lineages in vertebrate history. The fact that they looked like birds made it easy to underestimate them. The bones, as usual, tell a different story. From South America, and from the most recent entry on this list, we travel back 500 million years to a Cambrian sea, and the most spectacularly misidentified animal in the history of paleontology, Anomalocaris. The year is 1886. A paleontologist working the Stephen Formation in British Columbia finds a fossil of what appears to be a shrimp missing its head. He labels it Anomalocaris, Latin for abnormal shrimp, and moves on. A few years later, someone else finds a circular fossil that looks like a primitive jellyfish. It gets its own name, Peytoia. Later, researchers find a soft-bodied torso that seems to belong to yet another unknown creature. They call it Lagania. 3 species, 3 separate catalog entries, 3 separate places in the growing inventory of Cambrian life. The problem is that all 3 are the same animal. It takes from 1886 to 1985, 99 years, for anyone to assemble them correctly. When Harry Whittington of Cambridge University and his students, principally Simon Conway Morris and Derek Briggs, finally put the pieces together using the exceptional preservation conditions of the Burgess Shale, what emerged was not a primitive scavenger or a fragment of something simple. It was the apex predator of the Cambrian Ocean, the largest animal in a 520 million-year-old sea. An animal with compound eyes containing approximately 16,000 hexagonal lenses, a visual system comparable in sophistication to a modern dragonfly, in a period when complexity of that kind was not supposed to exist yet. This is Anomalocaris canadensis, and its existence forced a revision of what the Cambrian explosion actually produced. The body plan of Anomalocaris combined flexible lateral lobes running the length of its body for swimming propulsion, a pair of spiny frontal appendages used to capture prey, and a circular jaw constructed from 32 interlocking plates. Early researchers who examined the jaw in isolation argued that it could not close to a flat plane and therefore could not process hard prey. Later biomechanical analysis showed that it was highly effective against soft-bodied animals. The gut contents preserved in Burgess Shale specimens contain compacted material consistent with soft prey, supporting active predation rather than scavenging. The animal was doing precisely what its anatomy suggested. The compound eyes were formally described in a 2011 paper in Nature by John Patterson and colleagues, based on isolated eye specimens found in the Emu Bay Shale of South Australia. The 16,000 lenses they documented placed the visual capability of Anomalocaris above most modern arthropods in a Cambrian ocean that was, according to prior assumptions, populated primarily by animals with primitive or no visual systems. The eyes alone reframed what the Cambrian arms race looked like. If Anomalocaris could see in that resolution, everything it was hunting had reason to evolve defenses against a predator that could perceive them at distance. Some researchers have suggested that Anomalocaris itself may be one of the engines of the Cambrian explosion, the selective pressure that drove everything else to develop shells, spines, and eyes of their own. The misidentification history spanning 99 years was a product of how Cambrian fossils preserve. Soft tissue decays. Bodies come apart. Isolated fragments without context are genuinely ambiguous. The resolution in 1985 was not a simple oversight corrected. It was a genuine scientific reconstruction requiring exceptional material and exceptional analysis. A 2014 study by Jakob Winther and colleagues identified Anomalocaris as a stem group euarthropod, not a true arthropod, but on the evolutionary lineage that led toward insects, crustaceans, and spiders. It was not a dead end in that sense. It was an ancestor of things still alive today, but the question that sits at the edge of the formal literature is the one about disappearance. Anomalocaris and its relatives, the radiodonts, had near global distribution across Cambrian seas. Sites in Canada, China, Australia, and Greenland have all yielded frontal appendage material, which is among the most commonly found Cambrian predator evidence. And then, at or near the Cambrian Ordovician boundary, roughly 485 million years ago, they are gone, not diminished. Not transformed into something else recognizable. Gone, with the completeness that characterizes so many of the animals on this list. One interpretation, held by a small number of researchers, is that Anomalocaris was so successful as a predator that it drove an evolutionary arms race in which its prey eventually became too well defended for the original hunting mechanism to sustain. The predator optimized its ecosystem and then could not keep pace with what it had created. If that is what happened, it is the most remarkable possible outcome. The most sophisticated predator of the Cambrian Ocean may have been undone by its own success. We will probably never know. The fossil record ends the conversation before it reaches a conclusion. The claw without a body. The spiral saw without a jaw. The skull without a rear half. 10 animals, 10 missing pieces, 10 moments where the evidence said something should not exist and was right. Look at what connects these 10 animals. A buzzsaw jaw that stumped scientists for 125 years. A sea scorpion reconstructed from a single claw. A millipede that forced a revision of what carboniferous atmospheres could produce. An armored fish whose posterior anatomy has never been clearly preserved. A snake that rewrote the climate models for an entire geological epoch. A whale with the largest teeth in the history of life positioned where no whale's teeth were supposed to be. A crocodilian whose bite force exceeded any prey it is documented to have encountered. A pliosaur whose preliminary size estimates were publicly attacked before the formal paper existed. A bird whose killing mechanism biomechanists initially said would shatter its own skull. And a Cambrian predator that spent 99 years misidentified as 3 separate and unrelated species. The pattern is not size. Plenty of large animals have been accepted without controversy. The pattern is that each of these animals violated the mental model scientists had already constructed for its era, its environment, its body plan. The Cambrian was supposed to be simple, The Devonian Ocean was not supposed to produce an armored fish whose jaw no one has been able to replicate in any living lineage. The Paleocene tropics were not supposed to be hot enough for a 13-meter snake. The Norwegian Arctic was not supposed to harbor 3-meter skulls. In every case, the animal existed before the explanation did. The mainstream response, in every case, was ultimately to revise the model rather than dismiss the evidence. That is science doing what science does. But what these 10 animals collectively reveal is how often the initial resistance came not from contradicting data, but from the discomfort of a reality that arrived before the framework was ready for it. The bones were right, the calculations were right, the models adjusted. The fossil record is not a complete archive. It is fragments, preserved by accident, interpreted by inference. Every reconstruction is an argument built on incomplete evidence. If 10 animals this extreme survived in the record, the honest question is how many didn't? How many body plans left nothing behind? How many apex predators of their era dissolved before the sediment could preserve them? And how many of our current assumptions about what ancient life could and could not produce are quietly wrong in the same way the Anomalocaris catalog entries were wrong for 99 years? Most people encounter these animals in museums, read the label, and accept the approved version. They see the reconstruction and assume the reconstruction is complete. You are not that person. You stayed in the room long enough to hear what the labels don't say. This channel exists for the people who want to know what the argument looked like before the consensus hardened. Hit subscribe and stay in that room. Now go to the comments and tell us which animal on this list you find the most genuinely difficult to accept, the one where even after hearing the evidence, you still feel the explanation is not quite enough. Make the case. The floor is yours. The fossil record is a graveyard, with most of the graves unmarked. For every Anomalocaris eventually assembled from its misidentified pieces, for every Titanoboa pulled from a Colombian coal mine, there are animals that left nothing at all. No bone, no impression, no spiral of teeth pressed into limestone. They existed, they hunted, they vanished, and we will never know their names. The animals on this list are the lucky accidents, the rare moments when something impossible left just enough behind to be found, misread, argued over, and finally, barely understood. The bones were always right. We just had to learn to read them, subscribe, and keep reading.